Volume, volume. You folks here in the back? How's the volume in the back? Is it okay? Thank you. Hello. All right. Welcome back, folks. All right, let's get started. So for today, I just want to put up an announcement for an event this evening that may be of interest to some of you. Those of you that are interested in potential careers in graphics, maybe, for example, in movie making, this might be an event that could be of interest. It's at 4:30 this afternoon. Some folks from Disney Animation Studios will be on campus, and in connection with one of the animation classes, the UC Bug class, are going to have an event where you might be able to chat with them, learn about their process, and also talk with some of their talent teams about how they go about hiring and things like that. Okay, so keep that in mind. Recommend it if you want to go and check that out. A graduate of this class from a couple years ago eventually got a job at Disney Animation Studios and is connected with this effort. Okay, so today, the topic for today is going to be the rasterization pipeline, where we're sort of putting together a lot of the pieces that we've been talking about in rasterization, texturing, transforms, to talk about how like a high-performance graphics pipeline, like a GPU-accelerated graphics pipeline, puts it all together. But before we do that, I just wanted to go back to some things on and cover a few things about advanced texturing. And before I do that, I want to just rewind a little bit and note that Ben Mildenhall lectured, of course, on Tuesday about applying image textures to surfaces. So I want to cover a little bit more just to give you a taste for how texturing, applying, which we can generalize from putting image data onto surfaces. We can generalize that to bringing general data that we might want to lay over surfaces for repeated computations at the sample level. I'll talk about that in a second. But Ben talked a lot about these issues of how we can map coordinates in fragment space onto coordinates on an image space, a texture space, how we can pull color across. He talked about how that's something you can interpret as a sampling process in a way that uses a lot of the core ideas that we've been building up about sampling, signal processing, aliasing, and anti-aliasing. And then he talked a bit about how, particularly on the aliasing issue, it just shows up in a very powerful, very important way when you try to do texturing of this kind right away. And so methods for solving that aliasing issue, which you might see as moire or lots of texture artifacts, aliasing artifacts in the image that is laid on top of surfaces, just doesn't look right. Doesn't look high quality. He talked about how filtering methods for anti-aliasing are crucial. Talked about bilinear interpolation. Talked about downsampling, finding the right resolution of an image to put onto a surface, onto a patch of a geometry on the screen. Talked about how the sampling rates between those two and matching those is really crucial, right? And then talked about MIP mapping, a way of sort of getting a pyramid of images at different resolutions, lower and lower resolutions, gives you a data structure that can be really convenient for implementing one type of really common anti-aliasing for textures, which is called trilinear interpolation or MIP mapping, okay? So that's a sort of bundle of ideas. Bring image data onto surfaces, understand it's a sampling process, and then understand all the aliasing issues that arise and think about how to anti-alias in that realm, okay? Before I just give you a whirlwind tour of advanced texturing methods or different kinds of data that you can bring over, any questions that came up for you from the previous texturing lecture that I can try to answer before doing that? All okay? All right, great. And let me go on to the end of this lecture that Ben did almost all of. So he finished up talking about some anisotropic filtering, how trilinear interpolation with MIP maps can cause some overblurring as sort of one of the core trade-offs that happens in MIP mapping. MIP mapping is still great, really useful, very common. But there are other advanced kind of methods that you might use on subsampling this or downsampling, pre-filtering this image texture data. This is sort of an anisotropic downsampling method. So this was the last slide that he got to, and then I'm going to do a little bit on advanced texturing methods, okay? So high-level bit, I already said it, is that we first looked at putting image data, 2D images, onto surfaces, but there are many, many uses for texturing. And in fact, the whole term texturing, as it's used in modern graphics, is really kind of a bit of a confusing term. It's kind of a misnomer. You know why? Because it comes from image texturing, from image mapping, okay? That's sort of the history of how it emerged. But generally, how textures, quote-unquote textures, are used in modern graphics is just think of it as bringing data, bringing multidimensional data, sample data, into the graphic system so that when you're doing a computation at a particular sample, for example, for a sample that will eventually be in a sample buffer that will go to the screen, and you try to do a little computation in there, for example, a lighting calculation, which we haven't talked about yet, but I'll cover today. The inputs to that calculation, the data that you would bring in there, could be represented in multidimensional, quote-unquote, textures, multidimensional signals, okay, function data. So you can do environment lighting methods for it to illuminate your scene as if it was under different lighting conditions. You can store microgeometries, so instead of like having millions of triangles describe a very detailed surface or a mesh. You could have a coarse triangle mesh and then store some of this additional geometric detail in images. You could have procedural textures, so maybe this multidimensional data is not even tabulated as a bit of memory, a data that's in memory. Maybe it's a function that is a very simple procedure, simple code function that you could execute very quickly to compute the values of a multidimensional function. I'll show you some examples of that. You can do solid modeling with it, where instead of taking an image and putting it onto geometry, you can imagine the geometry sits inside a solid texture, a volumetric texture, and so you're picking up the values on a surface as if it exists inside, like maybe a material that's made out of wood or stone or something like that you've modeled. And that also leads to things like volume rendering, where the data may come from, that's very related to the solid modeling, except maybe in volume rendering the data comes from, for example, a medical data set, like a CT scan and MR data set. Okay? So let me go through some of these visually and give you a sense of what this means. Okay, so an environment map. Okay? Here's a function on a sphere. So what does that mean? It just means a function that's defined for every point on a sphere surface. Okay? And you could unroll that, and we could have latitude, longitude. You could have you could have like a polar coordinate map for that. In this case, it's shown as a latitude, longitude texture map. So it's a 2D image, but it's really that just defines a function that's mapped on a surface. And then on the right-hand side, you can see a rendering. Okay, so it's a teapot, and if you look closely at the teapot, it looks shiny. And you can tell it looks shiny because you see the reflection of the environment in it. And this environment, if you forget the thing on the left and just look at it, evidently this environment is a room with a couple windows that have, slats in the middle of the windows, dividing into quadrants. Okay, it's very clear visually. So, how would you calculate something like this? So, this is, if you think about it, very different than putting an image onto simply texturing an image onto the surface. If you did that and re-rotated this teapot, it wouldn't look shiny, right? It would look as if it had like these little reflections on it, and the reflections would stick on the surface as you rotated it, right? In this case, the computation is different. We're doing some calculation knowing where the viewing direction is, looking at the teapot, and for every position on the teapot, we calculate in a small function, a little bit of code that you can compute, a sample or fragment shader program is what it's called, a fragment program, which runs for each sample. You could calculate, what's the reflection direction? And if you imagine the world around this teapot as a really large sphere, that would give you an intersection point, that reflection direction onto the sphere. What's the value on that sphere? You could look it up in an environment map, a spherical environment map, like this latitude, longitude map. Okay? That can also be thought of as texturing. Why? Because we're just bringing data into the program. But very different, if you think about it, than simply putting it over it like a sticker. You could represent spherical environment maps in different kind of ways, as latitude, longitude. This one's a different representation that's based more on how a spherical ball, a mirror ball, might look if it was in the real world. Here's a terrific drawing by M.C. Escher that explored this kind of idea, like a gazing ball is sometimes what it's kind of look like, what it's described as. And on the right-hand side, you see mirror gazing balls that were taken photographically. This is work by Paul Debevec, who was a graduate student, a PhD student at Berkeley, and was for a long time a professor down in Southern California. And what he did was he took pictures of a mirror ball. In fact, he took many pictures at different exposure levels because sometimes the sky is a lot brighter than the dark parts of a scene. So he took many pictures in order to create a radiance map, which is a map of the intensity of light going in every direction. And one thing about a gazing ball is, if you think about it, it will give you the amount of light going in every direction of the environment because there's always some kind of point on this gazing ball that will reflect in all directions on the sphere, except for the part directly behind the spherical ball. Okay, it sort of blocks that particular direction, but it's small compared to the totality of the environment. So you have methods to try to capture this information, and then you could bring it into your program just like this, except now you're using photographic environment data, not a simple cartoon drawing. Yeah? Oh, great question. The question is, how come you don't see the camera in these environment maps? Yeah, you notice that? So in Escher's drawing, it's what it would look like in the real world, right? There's a picture of the artist looking at the gazing ball as he's drawing it. So you see the artist in there. On the right hand side, you don't see the camera. And this turned out to be one of the important things that you have to figure out how to do correctly if you're going to use this method. So you actually take two pictures of an environment, one of the gazing ball and then from 90 degrees, and then you stitch out. And so, so you get a reflection of yourself, but in different directions, and then you have to stitch it out as one of the methods. Good question. So if you use an environment light of that kind, you could imagine bringing it into an artificial scene, as you see on the right-hand side, and then doing something where on the middle you see there is like a glass sphere. You can see a reflection of the environment as well as refractions through the glass sphere of the environment. There's a bunch of little material balls there of different types, evidently some kind of polished marble or like different metal balls or glass balls. So you can imagine what would those objects look like if they were inside an environment map. Okay, and this is mixing image-based computer graphics with texturing and with the rasterization or the sampling techniques that we've talked about. Okay, this is another example. All of these are really just to give you a flavor for the many things that people have done to try to bring these kind of data into graphics programs. You could represent a spherical map instead of as a gazing ball image or as a latitude-longitude texture map. You could represent it as something that's called a cube map. It is pretty simple. As you can see here, a sphere, if you imagine it inside a cube, every direction projected from the center of the ball out onto the sphere would hit somewhere on the cube map too. Okay? So if you just imagine putting images on the surface 6 faces of the cube, that would also define a spherical function. Okay? Or you could define a spherical function that way. And this is sort of nice because it turns out you could come up with, if I gave you a vector and said, what is the value of my spherical function given this vector, you could imagine that there's some hardware, for example, on a GPU, that takes that direction and maps it to a particular pixel inside one of the 6 faces of a cube map. You could really accelerate that, okay? And that's done. So cube mapping is one of those kinds of things. And the other thing is it's kind of nice because you can really render this cube map in your program. So let's think about that for a second. I have, say, some kind of object inside a virtual environment, and then I want to light it. Maybe it's shiny, okay? I want to light it and its surface reflections, its shiny reflections, as if it's inside that world. But how would I know what the spherical function of the world is? I can't take a gazing ball picture of it, right? I wouldn't know what it is up front. I couldn't just make one texture map of it because it's totally dynamic. It depends on where that, for example, shiny car is inside like a racetrack or something. So what you could imagine is going to the position of that object in that world and looking in each of the 6 directions and then rendering the world from each of those 6 directions. And each of those images could be put onto the face of each of the 6 faces of this cube map. That could be a pass 1. So now you got a cube map. Now you render that object like a shiny car in there and use this environment map and this kind of reflection technique that I described in order to give it the reflections as if it's sitting inside that world. Okay? So these are some of the techniques that people have tried in order to bring these kinds of data into real-time graphics. Here's an example of not a rendered one, but here a picture taken inside a church in St. Peter's Basilica, actually, in Rome, and then remapped. So this was a gazing ball image, but now it's been remapped into a cube map, so you could put it into a graphics program with a GPU that has cube map lookup acceleration and use it that way. Okay, so a lot of these functions can be just represented in different forms as part of what you can take away from this sequence of examples as well. Okay, switching gears away from spherical functions, other uses of textures, you could do displacement mapping. As I said, you could store microgeometry about your scene. Instead of storing it in like a very detailed triangle mesh, you could imagine trying to store it in texture. Again, in terms of in some kind of sampled function is the way to think about it. Okay, but the term that's used in graphics is texture. Okay. In this case, the texture, instead of storing a color on a surface, could be actually storing some kind of perturbation of the surface position relative to a simple a simplification or a smooth estimate, a smooth approximation of that surface. So here, for example, in the top left, you could see a base surface described with a bunch of smooth surface components. A couple of lectures from now, we'll be talking about smooth surfaces and curves, how you represent those mathematically. And so this is described using some of those methods. But as you can see, it looks really perfect. It looks too perfect. It's been one of the historical problems in graphics is that the lighting looks real, but the world just looks too polished, okay? So a texture could be used to sort of bring some of the dirt and some of the imperfections of the real world in there. So you can see on the right, top right, some kind of displacement map. It looks a little bit like, what does the black and white mean? It's sort of, you can think of it as like a perturbation, amount of perturbation along the normal vector of the orientation of the surface is, how far out it's bumped in or out, how far it's displaced, what's called a displacement map. And then on the bottom, you can see a rendering of it where the surface that's rendered is, the geometry is described by the smooth surface displaced by this texture image. Okay? Okay. So that's one thing you could do. Here's a very different method. Let me describe it, and then we'll come back. It's sort of similar to displacement mapping, but the first thing you'll notice if you think critically about this is like it just doesn't seem as accurate, okay? But let me describe it. So this is a method for rendering evidently bumpy surfaces. Here's like a sphere that has a bump map on it to make it look like kind of the wrinkles that appear on an orange. And you can see an example of the kind of texture in the bottom left here, okay? But the difference here is that unlike displacement mapping, where we actually, in the graphics program, want to move the position of the surface according to that displacement amount, in this case, all that's happening is, and this is a little subtle, okay? What's happening here is you take the normal position of the surface, so which direction the surface is pointing, and you don't move the surface at all. You just like displace what the surface normal is as if the surface was a little bumped out so that it was pointing in that direction. So you don't change the position of the surface, but you sort of change its the surface normal that we would use in calculations of lighting on the surface. As you can see, if you do that right, it can look very effective. I mean, you might say, well, if you have displacement mapping, why would you ever do bump mapping? So bump mapping has been way more common in real-time graphics, and displacement mapping has been way more common in offline high performance, like movie-making kind of graphics, okay? Historically speaking. A lot of these things have gotten faster, so these days maybe displacement mapping is starting to make its way into more even real-time things. But I think this shows you kind of the trade-offs that people have struggled with because graphics is very high performance, a lot of computations are required, so a lot of approximations have to be made to get it to run in a reasonable amount of time. And you can see over here kind of what's going on. So here's some geometry. Some kind of sphere. Here you see a bump map version, and here you see a displacement map version. Okay? And if you look at them, okay, a couple things will be evident. First, this does look bumpy. Okay? But if you look on the periphery, the bumps that appear inside the interior visually are not on the edge, as you can see that they are here. So you can see this actually has displacements to the geometry. Also, if you look closely, this object is actually sort of shadowing itself. What do I mean by that? We'll talk a bit more about shadowing versus shading, but here you can see that the nature of the lighting on this periphery here, part of the surface, in terms of where it's looking at the light, the surface mesh is actually displaced outward, so it's blocking part of the surface from the light source, whereas on the sphere that's not going to happen because we're just perturbing the interpretation of where the normal vector is. Okay? Okay. Perturbs normal, perturbs positions. Okay, moving on to another type of texturing, continuing the sort of flavor tour. This is a solid modeling and procedural modeling in one example. So here you can see two objects that are evidently carved out of marble. But what's going on here is that there isn't a texture as an image that's being pasted on top of the vase here or on top of the ball. What's actually happening is there's a description of a 3D volume that has the kind of material properties of marble, in particular the changes in color here, okay, described in 3D space. And then when we put this ball or this vase into that 3D space, so what's the texture mapping? Here the texture is 3D, so we call this a 3D texture or a volume texture or a solid texture, okay? Think of it as a 3D function. And the positions on the surface will index into that 3D function. And this mapping is really simple, because it's just basically the XYZ coordinates of the surface positions on the sphere or the vase, okay? So you just look it up, but then you want to pull that data from a 3D function and bring it onto the surface. You could think about the kind of filtering methods or the aliasing or anti-aliasing methods that you might need in 3D. They're very similar to 2D, okay? Question, yeah?
Alex, would this 3D model be kind of similar to a thick block of marble?
Yeah, great question. So Alex asked, is this 3D function kind of like a solid block of marble? And that's exactly the right way to think about it. Okay, that's what the modeling representation here, or the designer of this representation for this vase and sphere is trying to accomplish. Let's describe a material, and then let's like carve objects out of the material. Okay? Great question. So, but the other thing is, how is this function described? So we could tabulate it like an image texture, except have a 3D version of it. Okay? You need a lot of, you call them voxels instead of pixels, and you can tabulate it up. I'll show an example later from a CT or an MRI machine where that's exactly what we'll need to do. But in this case, another cool feature that's happened is that this doesn't exist in memory anywhere. Okay? The solid texture here is completely procedural. So it's defined by a function. So whenever, for example, in the sphere, think about what's happening. We're rasterizing the surface of that sphere. It's got an XYZ position. It ends up as like inside a triangle on the screen. We rasterize across it. We have samples. At those samples, we're going to want to pass through the information about the XYZ position on the surface of that sphere in 3D. Okay, so we have an XYZ coordinate. Then we want to say, oh, inside the volume texture, what is the color of the marble at this position? That's what we want to look up. So you could look it up to memory if you had it as a tabulated function. But in this case, there's just a little function that says, hey, I'm the marble XYZ function. Give me an XYZ position, and I'll compute a short bit of arithmetic and give you the answer. And so this kind of procedural function is called noise, okay? And it allows you to bring quasi-randomization, pseudo-random functions in order to create these kinds of randomized procedural textures. Question, yeah?
Nick, so are these shapes, the shapes of these objects, defined by triangle meshes, or are they like a continuous function, or what?
Oh, great. Good question. So Nick asked, are the surfaces of these objects defined as surface meshes, or are they described volumetrically? And in this case, so the answer when we start talking about geometry is it could be either, okay? And I don't know actually for this specific example, but the only requirement in this case is that we'll be able to generate samples on the screen that are positions on the surface and know what XYZ position it is. So I'll say for these, based on what we know so far, you would do this at this point in the course by just describing it as a triangle mesh function. Okay? Did I see another question over there? Yeah. Why would we choose to do this over as opposed to just putting a mesh over it?
Because I feel like this, if it wasn't like some function, wasn't some like Cstfr that you're using, and you had to store a bit of information, then this route is like that would be a lot more.
You're absolutely right. So the question is, so compared to this image texturing that Ben spent most of the time last time laying the foundations for how texturing, filtering, anti-aliasing works, if you could just have the description of the color of the marble on the surface and just paste it on, you could store it as one image rather than storing a volume, which the observation is that storing that volume would be a ton more data. It's way, way more data, okay? And that's why in this example, it's done procedurally, okay? So if you had to tabulate all the volumetric data, that's a big trade-off in space and memory requirement. So in this case, there's a different trade-off. You do more computation. You do this procedural function for every sample, XYZ sample to get the color, but you accept that cost, and then there's no memory storage at all. Okay? So different trade-offs. Okay, continuing down. So you could also define certain pre-computed data, bits of data that might be expensive to compute. Pre-compute those and then bring them into your program as textures. So this is like it's a 2D image, but where's this 2D image coming from? You start from like a mesh, okay? And I'll talk about simple shading today that doesn't cover things like shadowing or interreflections. It's just that every point on the surface will do a very simple vector-based calculation of where the lighting is, where the viewing direction is, and where the surface is pointing. And just from those and a couple of material properties, how diffuse it is, how much it reflects light diffusely, how much it sort of reflects light shinily, we can compute a simple procedure that will give us like the shading on the left. But if you notice the shading on the right, it just looks more realistic. For example, in the nostrils of this character, it's very dark on the right-hand side, which is what you would expect. On the left, it doesn't. And part of that is computing that kind of shadowing is much more difficult. In general, probably require like a ray tracing system. which we'll cover later in the course. So you could pre-compute, using a ray tracing system, some of the shadowing effects over this geometry, and then bring that, in this case it's called the ambient occlusion, okay? The ambient, well, anyway, I don't have to explain the term. It's called an ambient occlusion function, and you can store it as a texture map and then bring it into your real-time graphics program. Okay? So you can even imagine pre-computing lots of things using other parts of graphics to pre-tabulate data. Okay, volume rendering. So before I described how you can make like solid objects as if they're carved out of different materials, talked about procedural volumetric textures. In this case, this is real data, okay? You can't come up with this with a procedure because it's measured, in this case, from a CT scan. So what you're seeing is a CT scan of somebody's skull, and then it's rendered, if you look at it, in a manner that's pretty interesting. It appears as if the skull is solid and opaque. And in this version, it's a little hard to tell, but in this case, it was modeled to look as if it's made of metal, okay, like a sort of a matte metal. And then if you look closely, you can actually see the surface tissue, the surface of the tissue, the skin, the profile of the nose, and it looks volumetric, almost as if that volume is like partially transparent, okay? And how this is rendered is actually using some of the simple shading models that I'm going to talk about next in the graphics pipeline, but it's done in a volumetric way. So we're taking a lot of samples through this volume and then accumulating them, semi-transparent volumes, and then accumulating them and blending them from front to back. And you can get a sense of how that's done on this diagram on the left. So what you do is you take a cube, which is this MR data set volumetrically, and then we're looking at it, say, looking down from one of the corners. So you can imagine rotating this head in space, right, and viewing it from different directions. So let's say in the top left here, we're viewing it from the orientation looking down one of the corners. We can draw samples, little polygons that cut through this cube from back to front. When we draw each of those triangles, they cut through this volumetric texture. We can pick out the value of the CT scan there, and then we can make some decisions. This would be like artistic decisions about, okay, where are the boundaries between skull and skin? It'll be sort of like different density values in the CT scan. How do we want to define what those materials look like? Are they made out of metal? Are they semi-transparent? So on and so forth. And then we can calculate values for each of those samples volumetrically and then accumulate them from back to front. Okay? So this is what is done in this volumetric case. I left a lot of detail out there trying to give you the high-level idea. Okay? But this is another method, instance of advanced texturing. Okay. You could talk about bringing data into graphics programs and how you would try to avoid aliasing issues, or how to filter correctly. You could spend, and people do, spend huge amounts of time on different creative uses of that and engineering it right. But I want to give you a little whirlwind tour for some of the most common ones. All right. Let us move on to talk about the rasterization pipeline. Okay. Okay, so what have we covered so far in the class, okay? We've talked about how we can position objects and the camera in the world. And so far, we've only talked about geometry as basically like triangles in 3D space, triangle meshes, okay? But even the details about how you represent that, we've sort of been a little hazy on. It's sort of given to you as XYZ coordinates. How we model that is something we'll talk about in depth when we talk about geometry. After that, we talked about how to compute the position of objects relative to the camera using transforms. We talked about how to transform those triangles from object space to world space to camera space, finally to screen space. And then when those objects are on the screen, each of those triangles, we talked about how to rasterize it by sampling the coverage of these pixel samples within those triangles. Then we talked about how to interpolate triangle attributes like colors or texture coordinates across each of these little tiny triangles. And then we talked about how to sample using, if we did texturing, using those texture coordinates into these 2D function representations, these texture maps, to pull that image data onto the map, okay? So that's what we've covered so far in the class. So what would that get us to, or what would we be missing if we tried to render, look at this here, if we tried to render a bunch of cubes using these techniques that we have discussed so far, I guess without advanced texturing. I mean, if you pre-compute textures and slap them on, then you get one thing. But if you try to do a rendering of, 25 cubes rotating in space, then you would get something that sort of looks like this, okay? So what sort of, this looks okay, sort of right. And then it sort of starts to rotate here, and then it just looks weird. Like, what is going on there? Okay, let's see. As it rotates over here, the bottom part looked okay, the top part looked really weird, and then the cubes look like they're glowing. Okay? Sort of, I guess. Sort of glowing. And so that leads into some of the things I want to clean up today. What the things that are going wrong here, at least two things are going wrong here. Number one is that the ordering of these objects is totally wrong as they're drawn on the screen. So if you look right here and look in the top left, okay, as it comes here, look in the top right now. Okay, the blue cube, which is off in the distance and further, is somehow being drawn on top of the yellow one. Okay, so what's going on there? The visibility of this is wrong. The occlusion of this is wrong. So visibility is something we'll talk about today. The second thing is shadowing. Okay, so if we draw it now as a solid object, and there's two things that changed here. One is the visibility was handled. So closer things are drawn on top of further things. And number two, each of the faces of the cube is drawn with a slightly different light level, okay, a brightness. And this gives the appearance, a very clear appearance of three-dimensionality by an implied light source that's shining on this scene, okay? So the two things I want to cover today are visibility and a simple lighting reflection model, okay? All right. So, but what else would we be missing? Okay, so visibility, like some shading models. If you look at this, which is a rendering, but this is done with a ray tracer. So what else do we see in this kind of a scene? Okay, so one thing is that there's a ton of geometric complexity here. Okay, you can look at like the folds on this modeled piece of cloth in the background. You can look at the kind of bubbles on this like hot chocolate foam. You can look at like the tiny little dimples on top of that yellow custard, okay? There's a ton of lighting detail. You can see reflections of like some kind of window on this white porcelain in the foreground. You can notice that there's shadowing there's sort of multiple shadows of these spoons onto the table surface. If you look very closely in the zoom in on the right-hand side, you might notice that there's depth of field. Just think of it as lens blur. So it's focused on the cup, but if you look in the background, like the lens focus is a little bit off, so it's kind of blurry in the background. So there's a lot of visual detail in this that we haven't gotten to yet, okay? Here's another example, okay? So this is also modeled. And in this case, there's also this lens blur effect, but there's also a motion blur effect from the movement of these wings. There's very detailed materials that are different from these sort of fuzzy petals to the kind of micro fur that's on top of this hummingbird skin. Okay? So what else are we missing? Surface representations, objects in the real world exhibit, highly complex geometric details. The lighting and the materials, the appearance is a result of how the light sources, which we didn't see directly in either of those rendered images, light sources which are off screen in those cases, are entering the scene, reflecting off those materials, actually bouncing many times in between those materials before those photons of light arrive at the camera. And then there's a camera model. So real lenses create images with depth of field effects and misfocus or focusing differences across different parts of the scene, kind of like how our eyes work and how real cameras work. So these are some of the things that we're going to be talking about over the next few bits of the class. Okay, so where are we so far? We've been talking about rasterization pipeline. We talked about rasterization of triangles, transforms and projections, camera modeling, perspective maps, projections. We talked about texture mapping and how to think about that as sampling with its own set of aliasing and filtering engineering requirements. Today we're going to talk about visibility, shading, and how they go into an overall rasterization GPU-like or historically GPU-like pipeline. Okay. Then we'll talk about geometric modeling for a number of lectures in the class. We'll talk about lighting and materials, and in particular ray tracing and recursive ray tracing techniques for estimating those in a physically based way. And we'll talk about cameras and imaging systems. So that's kind of where we're going. Okay? All right. But for today, visibility and simple shading model. So let's talk about visibility. So the problem, as I showed in that simple example, we draw 25 cubes, but then if we just draw them in any order, so think about what happened there. We just took cubes in space, each of which was composed of 6 faces, each of which is maybe 2 triangles. Okay, so 12 triangles per cube. We had a list of 25 cubes, so we have this long list of triangles. And what we did was they existed in 3D space. In fact, they're rotating in 3D space. So there's some transforms on each of those objects. Nevertheless, in 3D, and then we have some kind of camera. We take each of those triangles, project it all the way down onto the screen, and then we rasterize it. So what went wrong? Well, many of the triangles are going to project to exactly the same position on space. That's what happened, right? At a certain rotation of that wall of cubes, the blue triangles on the blue square in the distance happen to project onto the same pixels as the yellow triangles on the yellow square in the foreground, right? Of course this is going to happen. And what happened, I guess, is that when we rendered that program, for some reason, just the ordering, the blue pixels, the blue triangles in the background got, were at the end of the list, I guess. And when they got drawn to the screen, we decided that we would just draw them in and overwrite in the frame buffer whatever the yellow triangles were. Okay? So that's sort of mechanistically what would sort of happen. So what do we need to do? We need to figure out how to do this drawing or adjust this drawing so that visibility is respected, and things that are closer end up putting their values into the frame buffer and preserve their values in the frame buffer, even if we draw further things as well. So what are some algorithms we could use to try to do this? So let me just put this in a certain context. So early in the history of computer graphics, one of the most important researchers in computer graphics, Ivan Sutherland, was very interested in this problem, as was the entire community. And he's the person that's credited with inventing VR, okay, and as the father of computer graphics. And he wrote a paper that was 10 hidden surface removal algorithms. Hidden surface removal is just visibility. So if a surface is hidden because it's behind another one, then you want to remove it, okay? And they had a lot of algorithms for this. There are many, many geometric algorithms you can come up with to try to solve this problem. I'm going to talk to you about two today. In particular, because there's one that is totally one for almost all modern graphics kind of things, okay? But let me give you sort of the geometric one first, and I'll talk to you about the sampling one. The sampling one is the one that is one. The geometric one, you can think of as one of the simplest versions of it is a painter's algorithm. So it's very simple, okay? This is just how people tend to paint, okay? So how do you paint? You start from the back of the world, and you paint some stuff, and then you paint closer objects, and you paint closer objects, and closer objects. Okay, so let's see. So you have a scene here. It's got some mountains. So you paint the mountains in the background, and then you say, oh, well, actually, there was a sort of a meadow in front. So you paint that, and you overpaint part of the background. And then, oh, there's some trees on top. So you paint the trees, and you overpaint part of the meadow and part of the mountain. Simple, okay? So an algorithm for getting this right would be to just draw the triangles from back to front. Just draw stuff from back to front and overwrite whatever's in the frame buffer. And this will work great. This works great. Here's a cube, for example, slightly different. This one maybe a little bit less obvious because they interpenetrate. So let's say you got all 6 faces on a cube. So let's draw that one, and then which is the next one? You can draw this one, which is in front of the square in the back. I guess we can draw that one. That one's on top of some of those, and then the top square is on top of some, the side, left side and the back, and then there's the front. Oh, okay, all right. So we draw a cube, all right? So that would be painter's algorithm on a cube. Okay, so a couple of drawbacks of doing this that might occur to you right away. The first is you got to sort, right? If you're going to do back to front, you got to put them in order, in depth. And that ordering is going to change. If you do an animation and you fly your camera around the world and you have one big list of all the triangles in your scene, it is not the correct ordering for different views, right? Because the depth ordering depends on the viewpoint. So you have to do a sort in depth, which is O of n log n for n triangles. Okay, so there's a certain complexity cost there. The second problem is that if you start to think about it a bit more, this is a bit more concerning, you can have unresolvable depth order. Now this might look a bit like a corner case, but there's lots of objects you might want to describe where you could imagine this comes up. Here's a very simple one. Okay, so a constructed case, but here's 3 triangles. And by inspection, you can tell there's no ordering to PQR in a list that is going to execute the painter's the painter's algorithm correctly. And when you have complex 3D surfaces, then this will come up a lot. Okay, so what would you do? This is why there's so many algorithms. You could look at this and you say, well, I tell you what, we will just cut up some of these triangles into smaller triangles. And sure, you could try to do that. So you say, well, P overlaps R, so we can find the overlap region. You guys are starting to implement, triangle inside-out tests. And you can sort of do some vector math to figure out line equations. You can solve this, okay? Find all the intersection points. Cut the triangle R up into smaller pieces. Some of them won't be triangles. Retriangulate those. You got a triangulate function in your starter code. Okay, and then boldly go forth. Triangulate everything and then draw. But you can see that the complexity here is going to get higher. And then you got to retriangulate. This is what makes these methods kind of hard. But good to know about, because sometimes what you care about is not drawing to the screen to do this visibility. You might care about this geometry for other things. There's a whole field connected to computer graphics and doing other things, which is called computational geometry. This would be an example of a type of computational geometry problem, okay, of which there are huge classes. Some of them very mathematical, some of them very practical but mission-oriented, for example, in modeling of scenes for other things that are not graphics-related, like simulation for building, finite element methods, things like that, okay? So it gives you sort of a flavor of the connector. That's one algorithm. The second algorithm I want to talk about is not a computational geometry algorithm. It's a sampling-based algorithm. What does this mean? And this is the one, as I said, that's totally won out in graphics, okay, for visibility calculations. This is the idea is very simple. We rasterize to the frame buffer or your super sample buffer. You can do this on a sample-by-sample basis. And in that buffer, in addition to the color of the sample that you've calculated, you also store the depth of the scene. Now, how do you know this? Well, the objects, the triangles exist in 3D space, so when we project it down to the surface through a object to world transform with perspective to camera coordinates, through all of those things, we keep the effective z direction from the camera position, and we store the z position from the camera's viewpoint with the sample as it goes down through the pipeline. When it gets to the frame buffer, we store it in a special field of the frame buffer called the depth plane, which is called the z buffer, okay? So the algorithm is called z buffer. And then we use it the next time that we rasterize something that goes to the same sample position. We use the existing z buffer information to decide whether or not to draw in there, okay? And when we do that, we can, for example, put in a policy that if there is something that's in the z buffer that's closer than the new raster position, just don't draw the new thing. So only draw into the frame buffer if your new z position is closer. And you will get something that looks like the image on the left, and the depth buffer will be something like on the right, where 1 is close, black is far in this visualization. So let's just sort of walk this through. It's not complicated. Let me just do it quickly. Okay, so during rasterization, you take each triangle T. We use the rasterization methods that you're trying to work on for the assignment, and each sample XYZ in this T, for your assignment, it's a 2D triangle, but in this model with transforms, it would be a triangle in 3D space. We take that XYZ, and for, okay, actually, I realize this. Okay, so for each sample XYZ in T, after all the transforms from getting it from world space through to camera space. So XYZ is in camera space, okay? Then if the Z here, this Z for this sample, is less than Z buffer is just a 2D image in the frame buffer, a 2D plane in the frame buffer. If the new Z is less than the Z buffer value for XY, then what do? Frame buffer XY, update the color, and in the Z buffer value, update the Z, okay? So this policy here, Z, is something that is going to do visibility the way that we want it for Painter's algorithm. Okay? Pictorially, so let's say you have a frame buffer, no values in it yet, represented by R. We draw a triangle in it that's at a depth of 5, okay? So we just copy it straight into the frame buffer. Draw in the triangle samples, put it at a depth of 5, and color red, okay? Then we draw another triangle, say that's this one here. And this triangle is not perpendicular in the world to the camera like the red triangle was. This blue triangle is tilted in the world. This is actually even more complicated than the Painter's algorithm conundrum that I gave. This one is two interpenetrating triangles. Two 3D triangles in space that are actually partially overlapping each other. So, and this triangle, this blue triangle, tilts backwards in depth. So How would you resolve that in a painter's algorithm? Sort of tricky. You have to cut them up along the boundary of intersection. In this case, you just go sample by sample. So you try to draw it in, and you can see here, if you look closely, 8, 7, 6, 5, 4, 3. Those are the depth values, okay? So you can see the way that it's tilting in space. So when you draw into the frame buffer, no problem. You just go in and point by point, sample by sample, you just say, is there a value in the frame buffer already? If not, draw it in, as you can see down here. For the places where it overlaps, you say, 8. 8 is further away, larger z value than 5. So don't mess up the values that are in there. They're closer. But in this part, there's a couple of samples here that happen to be closer because of the tilt of this triangle, and so you update those. Okay? Yeah?
For the values that are 5 on both triangles, how did it decide to do the right one?
Oh, good question. So, how would we keep the 5 or would we update it? So the technical answer is in this version of this algorithm, we had a little less than instead of a less than and equal. But really, to be honest, these are samples in space, so the definition of what happens right along that boundary is kind of arbitrary. The larger sampling, this will generate a very high frequency, very fast-moving signal in your final image. High-frequency signals should scare you when you're sampling at a finite frequency now. Okay, it's not finite sampling rate. So resolving that goes through all the same sort of issues we talked about. And this is an example, another example of why in graphics, supersampling in order to try to gather higher frequency information or to approximate an anti-aliasing filter is really common. So to resolve that edge better and get sort of blended colors along that edge, you could imagine supersampling it and averaging down. Okay. Great. Z-buffer complexity, it's linear in the number of samples you take, but in the number of triangles, it's also linear. So this is O of n for n triangles. So you don't have to sort the triangles anymore. So you just the list of triangles, just draw it to the screen, and everything will get resolved at the z-buffer level. Okay? Which is a pretty cool feature. Very brute force. If you're thinking like a computational geometry person, you might say this is kind of a cop-out, because you never really solve the triangle visibility issue, or the object visibility issue, but it works real well, and it's the most important visibility algorithm. Okay? Implemented hardware for all GPUs, used by OpenGL, other stuff like that. Okay, question? Yes. Hey, Joe. Mm-hmm. Oops, sorry. So you're asking, I'm having great. Today my video problem is finally turned up. Anyway, it doesn't matter. I was going to bring it up. Sorry for the distraction. Ask the question again. So you're saying with the average value? Yeah, so the question is, in this example where we're having this weird incorrect occlusion, incorrect visibility phenomenon happening, where the further cubes are sometimes being drawn on top of the closer one, what's happening there? And in this case, there's no z-buffer algorithm being applied. And so when each of the triangles gets drawn to the screen, it just draws into the frame buffer with an overwrite. So instead of if z is less than z-buffer of xy, that's gone. So it's just if true, draw into the frame buffer. And then what's going to decide the final color? It's just going to be which is the last triangle that was drawn to that particular sample. That's going to be the color you get. Does that answer your question? Yeah, good. Good question. Thank you. Okay. All right. Let me talk about simple shading. So the shading model I want to talk to you today about is called a Blin-Fong reflection model, after two of the folks that pioneered the use of this. There's a lot of different reflection models, reflection functions, approximations, as well as physically based ones in the computer graphics literature, because there's a lot of different materials, and it turns out shading is the most expensive part of graphics. It happens to have the highest density of computations typically for final things that you want to put on the screen. And so lots of approximations for efficiency and lots of study to try to make things look as realistic and accurate as possible to real-world materials. The one I want to show you is to start to build some of your intuition from some phenomenal, like the phenomenon of how different things look in the real world, so appearance-wise. And it'll be simple shading. And I want to contrast this with realistic lighting. So today, this local shading model is very simple, it's per pixel, it's very fast, and it's going to be based on looking at things and sort of asking at a high level, why do they look that way, and how might we approximate that, okay, mathematically. And this is to be contrasted with a physics-based model for materials or lighting, and how to compute in a scientific way, a radiometric way, what the number of photons at the end of the day. How many photons going through a realistic model of the world scientifically would have appeared in this final pixel behind this camera in this model world. That's going to be what we'll talk later on in the class. And that will lead us to global light transport is the name for that kind of simulation. Not local, very expensive, but very satisfying intellectually, and used all over now. Okay, it is now used in ubiquitously in offline rendering for movies, and I think we're at the cusp where it's about to take over for real-time graphics too, because we have so much compute now. We're right at that sort of boundary. Let's start with the simple model to start building some of our intuition. Okay, so let's take a look at this scene and start to think about why these plastic cups look the way they do. Or first, let's start with, how do these plastic cups look? Here's a few things that I'll draw your attention to. Okay, so it's like some kind of simple plastic type material. Each of these cups has a different color, and they kind of look shiny, right? And you can tell there's some kind of light off to the right-hand side because it's reflecting off this. So let's make a few observations about this. And here I'm going to start to classify a few things that may not be super intuitive if you're looking at it for the first time. But people have spent quite a bit of time trying to boil down why do these objects look the way they do, and what are the components involved, the simplest components involved in modeling how they look. One of the components is the diffuse reflection of a particular material. And this gives usually the intrinsic color appearance of that material. So in this case, the diffuse reflection for this yellow cup is a reflection function that will take white light and tend to reflect the yellow component of it, similarly for the other cups. And one thing about why it tends to look intrinsic is that color doesn't depend on which direction you're looking at the surface or the object from. It doesn't depend on which direction you look at the object or that point on the surface. Okay, so in general at the object, but thinking very specifically at one point on the surface, if I look at that cup from different directions, it will look yellow because that one point will always look yellow. At least the diffuse reflection part will always look yellow. Okay, so that's called the diffuse reflection part. Now, there's another layer on top of that, because if you think about what I just said for a second, you say, well, that's not true, Ren, because if I rotate it just right, it won't look yellow. It's going to look lighter yellow. It's going to look, in fact, it's going to look white at some point because it's going to reflect this window that's off to the right. That's not true. The second component is often described for these types of materials. The simple model is what's called the specular reflection, or the specular highlight. You can think of specular as just mirror. Okay, it's like a mirror reflection, although it's sometimes not like a perfectly shiny mirror. It might be a little bit a little bit matte. Okay, the degree of shininess or matteness is sort of a parameter, okay, for this component. But this part is the part that is reflecting the light and will dominantly look like the color of the light. And then in this simple model, there's one more component called the ambient lighting, which is a little bit confusing. We'll go through each of these, but this is sort of saying that, look, as will become clear as we model this, okay, if we only model the diffuse reflection, the part that is due to the direction of the light source and the direction of the viewer relative to the surface normal, or the direction that the surface is pointing, that sort of changes how light or dark it is, but not the underlying color. If we only had that, and we only had the specular part, which is sort of the mirrored reflection of the light, the scene generally will look very dark. Because if it has only one light source, anything that is blocked or not facing towards the light or reflecting into the direction of the light will be pitch black. Okay, so and usually the way that happens in the real world, why things don't never look pitch black, is that there's lots of multiple bounces of light. The window bounces off the table and bounces part of it back onto the onto the reverse side of the cup and so on. There's a complicated multi-bounce flow of light there that sets this overall lighting level. We need recursive ray tracing in order to get into how to model that. This is a per pixel. The only information you got is where are you on the surface and which direction it's pointing. So it turns out we'll need an ambient term that we'll add in there to hack around this. Okay, let's get further into this. So the local shading for each of these components, let's start with the local shading model, rather, is the things we're going to limit ourselves to compute this are as follows, okay? We want to compute the light reflected towards the camera for a piece of surface where we know the viewing direction, V. We know the surface normal, N. And for a curved surface, right, it's a tiny little patch, so you can think of it as like the local perpendicular vector to the surface. The light direction, L, in this case for a single light L. If you have multiple lights, it'll just do it for each of those lights and add it up, okay? Linear in the number in each of the lights. And then a bunch of surface parameters. I alluded to these. You got the color of the surface, you got the shininess of the surface, you got the color of the light, things like that. Okay? Okay, so let's get into it. So the first part is the diffuse reflection part. This is the light that is scattered uniformly in all directions. And as I said, it is the thing that gives the characteristic color appearance of the object. So what does it mean to scatter uniformly in all directions? So literally, we'll say how much light is falling on the surface. That's how bright it is. That'll be the number of photons, so to speak, per unit time that's falling on top of onto that tiny patch of surface. And then we're going to assume that those photons get scattered equally in all directions. If they are scattered in all directions equally, then, well, no matter which direction you look at that patch of surface, it's going to look exactly the same. Okay? By sort of by definition. But it will change depending on the direction of the light and the intrinsic properties of the surface. So how does it work? The first part, the relationship between the light source and its effect on the brightness or the appearance of this surface patch is given by something very, it's called Lambert's cosine law. Okay? This comes up in tons of radiometric calculations. We'll see it later in class as well. It's a pure geometric property. It's just a cosine law. So what is that? Let's just consider the brightness of this top surface of this cube. So imagine that you have the sun, okay? And the sun is sending photons. There's a certain photon rate. We'll just sort of approximate that by, or represent that visually by a set of rays here, each of these rays being some number, some flux flow rate of photons, okay? And then consider how bright is a patch on this, tiny patch on this surface going to be in this condition versus if we rotate it like this. And as you can see, well, you know, like half the photon, all the photons arrive at the top of the surface here, but that same volumetric flow here is half of them are missing because why? Because the tilt of the surface projected into that flow is half, okay? And what is that ratio? Well, you can work out the math a little bit. It's going to be exactly the cosine of this theta here, okay? So it's just what fraction of this area projected into the direction of the light flow do we have? And so this factor is going to be cosine theta, which can be written as n dot L or L dot n, where n and L are unit vectors. So if you have n and L, the surface normal direction, and the direction pointing to the light, and they're both unit vectors, then this ratio here, this cosine theta term, will be n dot L. Yeah, question? Yeah, the question is, so what do I mean by scattering in all directions? Does this mean that when the light hits the surface, it goes equally into all directions? And that's exactly what I mean. Okay, so how much light is falling on the surface is one of the key factors is given by this diagram here. After you know how much light is falling on the surface, and you want to know what's the color going to be in another direction, well, it really depends on how it's reflecting it. So if it's reflecting it like a mirror, all the light's going to go in the mirror direction, and if you're not in the mirror direction, it'll look dark. This diffuse component is the component that is modeled saying that we're going to assume any amount of light that falls on the surface gets scattered probabilistically, okay, statistically equally in all directions. If that happens, then for this component, when you look at that surface from different directions and you don't move the surface relative to the light source, a point on that surface will always be exactly the same color, irregardless of which way you're gazing at it. Okay? That is not physics, again. That is a modeling component based on this perceptual observations that we made before and how we're trying to dissect the different parts of this reflection. Okay? All right. The second thing is light fall off. This component is a little bit less important, so let me cover it quickly. Basically, if you try to model this is pseudo-physics. This is real physics, but it's since this is not a physics-based lighting model, and it's not physically coherent, as we will see later, if you try to put it into a total light flow system. This part is sort of just a constant factor. But one thing you can observe is if you have a light source that's out in space somewhere, and it's putting a certain amount of power, that amount of power as it radiates away is going to be equal on a sphere. So the intensity here is going to be equal to 1 over r squared of the intensity over here, just conservation of energy as you go out. So that's sort of an observation about that. Oh, I meant to take that slide back out. Doesn't matter. Okay, so Lambertian diffuse shading here, n dot L, you have this theta term, you have a certain amount of intensity coming out of the light source. The intensity of the light source is I, divided by r squared is the distance from there to the position of the surface, to the object. So this is how much illumination comes from the source to this object. And then we have the n dot L term here. And then you notice there's an additional, there's sort of a bit of a weird thing here. There's a max of 0 or n dot L, which might look a little bit weird, but let me just walk you through what this is doing. So n dot L here will be some fractional component. It's bright when the light is directly equal to the surface normal. Okay, that's equal to 1 n dot L. And then as n dot L, as this theta term increases, n dot L goes down fractionally. The light's arriving at the surface from a grazing angle. It will look darker and darker. Once the light source is perpendicular to the surface, it's coming from over here, okay? 0 amount of light is transmitted to the surface according to this cosine law, which makes sense because that surface has no projection into the flow of light. Once L starts to go here, so theta is more than 90 degrees, n dot L will be negative, okay, just like as vector math. So if you had a negative number here, we don't want that. That doesn't make any sense. It's not like the brightness of the surface is negative. So it's just clamped at 0. That's all that's doing, okay? Question, yeah? Yeah, that's exactly. At that point, the surface will be facing away from the light, and it will receive no light. Thanks, Peter. Yeah? A great question. So Lewis's question is, are we assuming that the light rays are parallel here, in which case there shouldn't be any fall off? And in this particular case, we're going to treat it as a point by point. And for each of these points, it's going to be a sample on a surface. So you can actually take the light vector as either being constant, in which case the light is very far away, and the L is a constant vector, or you could have the light source be local, close enough to the surface so that that L vector will vary over different surface positions. And then you calculate the L value in computing that. So it can be either local, that's called local lighting, or distant lighting. Good question, yeah? If you have multiple surfaces here, what's going to happen? Yeah, the light's going to bounce back and forth between them. That's beyond the local lighting model. We had to deal with this a lot in global illumination. That's one of the key problems in global illumination. We'll talk about that in recursive ray tracing later. Question, yes? N and V, okay, good question. So N is the normal vector to the surface. So N for this surface here, point out there. If it was a ball, N would vary continuously and would just point directly away from the sphere, okay? V is the viewing direction. So here's a little I. So when you think about from the viewpoint of the camera, okay, which V is that? Where's that surface position relative to the center of the camera, so to speak, okay? Say that again? So you'll notice that V is not used in this equation at all yet. We'll come to that in a second. Yeah, but it doesn't replace N. Yeah, those are two totally separate. N is intrinsic to the surface point, and V is where the eye point, where the camera is. Okay, good questions, thanks. And then finally, there's a coefficient here, diffuse coefficient. This is the color. Think of this as an RGB. It'll be the color and how bright, if it's yellow, if it's a bright yellow, or sort of a dark grayish yellow, okay? And so K sub D here, that coefficient there. If it's in grayscale, this is a low K sub D, this is a large K sub D. So it's just is it a dark sphere or a bright sphere color-wise? Okay. Okay. Next part. this Blinn-Phong model is called the specular component. So this is the component where the intensity depends on the viewing direction. Now we're using the v vector, okay? And the idea here is, actually going back to this, what again is this supposed to try to model is these specular highlights. These are the mirror-like reflections off the surface. It's kind of like the surface has like, in fact it does, underneath it has a shiny surface, polished surface. Underneath there's a rough kind of a paint, or rough kind of plastic material inclusion texture, maybe some kind of like inclusions inside the substrate of that plastic material. That substrate is causing the diffuse reflection. On the very surface, it's shiny, and that's causing this mirror reflection. And so the specular highlight is the portion that's sitting on top, reflected off that shiny layer that's creating this. And this is going to depend on the viewing direction because it's going to be, the surface is going to look bright at positions where the viewing direction is close to the mirror reflection direction. So what's the mirror reflection direction? Here's the surface normal. The light comes in, it's going to bounce off. This would be a perfect mirror. If it's not a perfect mirror but sort of shiny, it'll go close, mostly reflect very close to the reflection direction. And then the proximity of your viewing vector into that, the proximity of it to that reflection direction will dictate the brightness. Okay? Now, it turns out, so that's the idea. And if I told you that you could write something down, you could write an equation for the reflection vector in terms of vector math from n and n and L rather, and you can compute from there. It turns out, and you can go convince yourselves of this, you can use another thing that turns out to be very helpful mathematically to give a close approximation to this called the half vector. The half vector is the bisector between V and L. Okay? Here's L, the light direction. Here's the V, the viewing direction. Here's H, which perfectly bisects the angle between L and V. And it turns out that's nice because you can calculate H just by summing V and L. And all of these are unit vectors, so we'll just normalize it. Okay, so the normal unit length direction between at the sum of V plus L, half vector here is given by V plus L. Then the specular component, the specular reflected light in this Blinn-Phong simple local shading model, okay, is given by this equation here. So what's going on here? Okay, so it's got some components that are similar to the previous one. There's some K sub S. This is the specular coefficient. You can sort of think of this as the color of the specularly reflected component, that mirror light, like how colored does it look like, which for plastic materials will turn out to be 1. Okay, just like usually for dielectric materials like plastics, it fully reflects the color of the incoming light. For materials, this case, for metals rather, K sub S turns out to have the color of the metal itself. You can try to observe that as you look at different metal materials and different plasticky or dielectric materials now as you go around. Okay. Anyway, so K sub S is the color of the specular reflection. There's the same I over R squared term. And then here there's a cosine alpha and there's a P term. That's what differs. What's alpha again? Alpha here is this little angle here between the normal vector and the half angle vector. This is, alpha is the thing we're using to represent the proximity of the viewing direction to the mirror direction. If the viewing direction was exactly equal to the mirror direction of the lighting direction, then H would be exactly equal to N. Okay? And as the viewing direction deviates from the reflection direction of the lighting vector, the half angle H vector will just move away from N. So N dot H is just that cosine of this little angle in here, cosine alpha, and then we raise it to some p power. Now, why do we raise it to some p power? So the p power is just a way, mathematically, to represent how shiny the surface is. So if this is cosine alpha raised to p equals 1, then of course it just looks like a cosine. If it's cosine squared alpha, you can see it gets a little tighter towards the y-axis. Cosine to the 8th looks like this. Cosine to the 64 looks like this. Now, what does this represent? Remember, alpha, again, is how far away we're deviating the half angle vector from the normal vector, which is giving us how far is the viewing vector deviating from the reflection direction, the mirror reflection direction. Okay, so as alpha is getting, as cosine alpha rather is getting larger, we're getting further away from there. So we want it to go down because we're not at the mirror direction. And the rate at which this reflected component is going to go down is given by this. We have control over it by modeling it as this exponent. So raise it to higher exponent, we would expect it to look more shiny. Let's take a look at that, okay? So here's some surfaces that you can look at this. K sub S is here, very similar to K sub D. The higher K sub S, the brighter overall is the specular component, this shiny spot here, okay? P here, increasing this way, when it's small, you get a broad mirror highlight. And as P increases, you get a tighter and tighter mirror highlight. The higher P is, the closer your viewing vector needs to be to the reflection vector, the mirror reflection vector, in order for you to see this specular highlight. Okay? All right. And the last term, yeah, question? K sub S, you mean? Or it only controls the brightness. Only controls the brightness. No, yeah. I see what you mean. We can stare at it a little bit. We can come debate it. But the P parameter is the shininess, and the K sub S is how bright is the reflection. Yeah, Peter. Can you say that again?
Like, since we're using like the max function,
Mm.
diffuse and specular lighting until when it's like not used anymore.
Yeah. So the question is, since we're using this max function here, are we going to see some sort of like harsh cutoff? And the answer is no. The reason is that the cosine alpha, as well as cosine alpha to any power, will smoothly drop to 0. So we're just saying once that's 0, then once that drops to 0 and you start to go below it, then don't go negative. That's all it says. Good question. All right. So the ambient term I said is shading. Okay, so this is just shading that depends on nothing. As I said up front, it's just going to be a hack term in this model. And it turns out to be a really important hack term perceptually. All it is literally it's some coefficient called the ambient coefficient K sub A that just takes how much light are we putting into the scene and just multiplies it by some small constant and adds that to every position in the scene. Okay, so let's take a look at what that looks like. So here is some kind of weird bumpy shape. Here's the ambient term. It just takes the incoming light, multiplies it by some small number, and puts it over the entire scene. So you can see the outline of this, but it does not look shaded in any way. Second is the diffuse term. This is what it looks like, this n.L term. The diffuse reflection term, you can look at it and say, oh yeah, that looks like a diffuse blue paint, a matte blue paint. Here's the specular term. Looked at just by itself, it's quite hard to identify. It's mostly black, but it's reflections of the light source at positions where the surface is curved at just the perfect angle so that the mirror reflection direction is close to the light source. And if you put them all together, then you get this blue plasticky kind of material shape. Okay? So again, the diffuse reflection component giving the intrinsic color of the surface, which doesn't vary as you change your viewing direction. The specular highlight, which is highly view dependent, and as you move your view position, you'll notice that specular highlights on surfaces move over the surface very quickly. You can pay attention to that in the real world now as you look at the world after lecture. And this ambient term, a hack to sort of make things not look totally dark in the back. Okay. Yes? So say that again? It's going to be the specular component. So the question is, which part of this model gives the shiny component? It's this K sub S term here. This is the specular component of the Blin-Fong shading model. The overall thing is the Blin-Fong shading model. This is the specular component, giving this part here. This is K sub D, the diffuse component, giving this image here. And this is the K sub A ambient component, giving this. So this image is just the sum of all three. Okay. Let me talk a bit about shading triangle meshes. So when you shade triangle meshes, one of the issues which is connected to sampling is what's the frequency of sampling of the shading. And here I want to give you 3 different modes that practically you'll see will be choices for how frequent you can do this shading calculation in this kind of graphics pipeline. You can do it at the triangle scale, you can do it at the vertex scale, or you can do it at the pixel or sample scale. And this is rough terminology that is not historical, but it's called flat shading or Gouraud shading or Phong shading. And the thing you will notice is that this looks very segmented because we're shading each of the triangles with a flat color. This looks smooth in the diffuse component, even though you can tell it's the same coarse triangle mesh here. It just looks smoother in the diffuse component. But you'll notice the specular highlight looks a bit weird. It's undersampled. Okay, and here you can see that even the specular highlight looks cleaner. It's sampled adequately. Now, why is this? Over here, we're choosing the triangle and doing the calculation once per triangle and then drawing over all the samples. That's the simple sort of rasterization, constant color model that you're doing for part of the assignment. If you do it here, what we're doing is calculating the color at each vertex. What does that mean? The color calculations I showed you are all per point, right? So you could do it at each of the vertices of this mesh, and then we can give the color to that vertex in the mesh, and then when we color each of the sample positions in rasterization, we can interpolate the colors from the 3 vertices of each triangle according to barycentric coordinates, as Ben talked about last time, and you'll do in the assignment. In this model, you can sort of think about, well, what would happen here if we calculate the specular component? That takes the viewing direction and dots it with takes the dot product with of its half angle vector with the normal vector, right? So if we only calculate it at each of the vertices and blend it, this is what we'll get. It's very bright at the vertex, which is closest to the mirror direction, and then the other mirror directions over there are lower, so it blends off. But it's not high frequency enough to capture, because this is such a coarse mesh, it's not high frequency enough to capture the fact that this is a very tight dot. So in this case, what we can do instead is we can take the normal vector for the surface, for the sphere. We can take the normal vector at each of the vertices on the mesh, and we can interpolate the normal vectors across the surface using barycentric coordinates. We pass those interpolated normal vectors down to the sample, to each sample that we generate. We get a slightly different n vector at each of those, okay? And then we do the Phong shading model, the n dot h calculation at each sample on the surface. So it's happening at way higher frequency, once per sample over each of these spheres, not once per vertex, as you can see up there, okay? So this also allows you to see how in the pipeline there are different insertion points where you can do operations at different frequencies and think about which ones you would do. So in this case, probably the diffuse shading will work fine per vertex, but the high-frequency Phong or specular shading evidently in this case needs higher density and is done at the per pixel scale or per sample scale. All right, thanks, folks. We'll pick up there next time. Hey, Peter.